The next talk is from Clarinda from University of Cavendish, and she's gonna discuss about the beaming simulation for FRB. So yeah, Clarinda, please. Also, let's welcome our speaker.
Yeah, hi, I'm Clarinda. I'm currently a master's student at the University of Canterbury in New Zealand, but this is work I did from a summer project at Swinburne University in Australia, which was focused on beaming in FRBs, which I did under the supervision of Yogesh, who talked, I believe, just a few days ago. So the main aim of this project was to look at the directional dependence of the emission, which is what we call the beaming. And so by trying to reproduce observed energies of known FRBs, we can analyze how beaming may influence the energy distributions. And this theoretical explanation can help us to understand the role of beaming in the observed energy distributions, which can potentially help us to further constrain the emission mechanisms or the progenitors of FRBs. And so by modeling the energy distribution of FRBs, it is typically reliant on the cumulative distribution function instead of the probability distribution function. And so usually the cumulative distribution function is modeled using a power law, as shown in this graph here. And it typically has a power law index that ranges from about -1.1 to 0.2. So the burst energies of FRBs are typically between 10 to the 36 to 10 to the 41 ergs. However, the limits on the lower ends of energies observed are caused by a telescope sensitivity. And so the energy distribution we observe is also dependent on the number of bursts. So if there's an activity window with more bursts, then the energy distribution is more detailed. And if we, with both of these factors in mind, we can make the basic assumption that we are only observing the most energetic and the FRBs with the most bursts. So in particular, this histogram shows a window of activity from 12-1102 by Lee et al., and they found over 1,600 bursts over the span of about 47 days. And so they found a bimodality that appeared in a period of activity. It stayed for a number of days and then it disappeared. And they were able to model this bimodal burst energy distribution with a combination of a log normal function and a generalized Cauchy function. And they suggest that this may mean that possibly more than one emission mechanism or emission site or beam shape would be required to result in this type of energy distribution. Similarly, Zhang et al. Also did a study on 800 bursts from 2011-24A, where they also observed a bimodal energy distribution, and they modeled theirs with an exponentially connected broken power law function. And so both of these papers are trying to use more complicated functions to try and recreate the observed energy distributions. However, they are ignoring the fact of the beaming. And so we're going to try and recreate the same observed energy functions, but with beaming and hopefully simpler functions. So we consider beaming to be the effects on the observer's position relative to the center of the beam on the observed energy distribution. So we need to consider three main features: the angle of the observer relative to the beam, the shape of the emitted beam, and the underlying energy distribution. So firstly, we assume that we can just observe the beam from a random position angle. So to make my simulations, I started off by creating a sample of uniformly random X and Y angles that describe the position of an observer relative to the FRB. And so we exclude angles that exceed a maximum angle. And so past that point, you can't observe any emission from the FRB. So going back to this diagram, if the angle is in line with R0, then they will observe the maximum energy. If the observer is between Rp and Rmax, then they will observe some energy from the FRB. And if the observer is angled at a position greater than Rmax, then they will not be able to see the FRB. And so based on the current literature in FRB beaming, we chose two main beam shapes, which are Gaussian and relativistic. And so the graphs I have here are the beam strength on the y-axis and the given angle from the center of a beam on the x-axis. And so then using our randomly positioned observers, we can generate observed energy distributions as shown in the top row of graphs here. So we also consider the case of a simple isotropic beam. So it's just one energy observed no matter your angle from the FRB. So the definitions for our beam shapes are also above this corresponding graph. And you can see that from the relativistic beam, we also have to consider a Doppler factor. And we also have to simulate a secondary angle value theta, which is drawn uniformly between -1 and 1. So we are able to combine the isotropic beam and the Gaussian beam with the isotropic beam with the Gaussian beam and the relativistic beam also with the isotropic beam to create a combined beam piecewise. And this gives us a plateau region in the observed energy histograms. So at an angle greater than RP and less than the maximum angle, then the observer will get either a Gaussian distribution or a relativistic distribution, or if they're at an angle less than RP, then they will see the maximum energy. So from looking at these energy distributions, we can see that the Gaussian beam gives us a sort of uniform distribution, but the relativistic beam gives us a distribution that resembles that of a power law. And we also considered a set of intrinsic energy distributions. So we consider a single energy, a power law, and a long normal distribution. We also initially considered a broken power law, as shown on the right, but it had a similar effect to the single power law, and it didn't create any effects that would favor a bimodal energy distribution. And also through beaming, the effect of the broken power law was not conserved. And so for the rest of this talk, we've excluded the broken power law as it hasn't provided any significant difference to the single power law. So these graphs are just for the intrinsic energy distributions if there was simply isotropic emission. So I've also included our definitions for the power law and the log normal distribution below the graph. And so for the power law, we can change alpha, the power law index. And so with our definition, alpha must be less than -1, so that as E tends to infinity, the probability of a burst energy tends to 0. And for the log normal distribution, we are able to change S, which is the shape parameter. So going through all of these steps again quickly gives us our simulated results. So we first generate a number of observer angles, we then create a beam shape, apply an intrinsic energy distribution, and then we get out an observed energy distribution. So now looking at the different combinations of the intrinsic distribution of the beam shape. So there's quite a lot of graphs. So for the rows, we have intrinsic energy distributions and the columns are beam shapes. So this row is just having a single energy. The second row is for the power law intrinsic distribution, and the third row is for the log normal distribution. Then the columns correspond to the different beam shapes. So we have isotropic, Gaussian, relativistic, the combination of isotropic and Gaussian, and then the combination of isotropic and relativistic. So we will only really look at 3 examples because there's a lot of graphs, and these show the most interesting results. So for the Gaussian beam with the intrinsic power law energy distribution, we get a simple uniformist distribution with a power law-like drop-off at the top. We don't really care about the lower end of the energy distribution, as this drop-off comes as a result of telescope sensitivity. And the interesting thing about this is that the resulting power law slope at the high energy end of the distribution comes up with the same power law index as that of the intrinsic energy distribution. But it doesn't give us any sort of bimodal distribution. So next, if we look at a Gaussian beam, but this time with a central core or a central isotropic region, we get a big spike in the higher energy end, but there is no clear secondary peak. And so from these 2 initial types of beam shapes, we can conclude that the Gaussian gives us a uniformish area in the observed energy distribution, and any observed energy distribution that has a second rise or a peak must have a beam shape that falls slower than a Gaussian. And so if we combine a central isotropic core with a relativistic fall-off and an underlying log normal intrinsic energy distribution, we are able to recreate a bimodal energy distribution. And so then, because we're actually able to recreate a bimodal energy distribution, we want to understand the relationship between the beam parameters and the observed energy. So we create a graph that describes the relation of the beam parameters, which is the X and Y labels. So the shape parameter from the log normal function, and the plateau size, which is the angular size of the central isotropic core. This then gives us an output of the log of the ratio of the high energy peak to the valley. which is a bit of a mouthful. But what it means is if we look at this graph here, we see the low energy peak, we have the high energy peak, typically between 10 to the 38 to 10 to the 39, and then we have a valley in the middle of the two peaks. And so if we take the log of the ratio of the high energy peak to the valley, then we're able to plot it on this graph here. And so taking these two known FRBs, we can plot them onto this graph, and then we can determine a range for their potential beam parameters. And so currently this graph doesn't consider errors or the time evolution of the energy distribution, but by fitting the actual model to the output energy distributions from these two FRBs, we can hopefully constrain the parameters further and determine how reasonable this is, and hopefully be able to help us refine the parameters a bit more. And so to summarize, we find that we can create a observed bimodal energy distribution using a combination of a relativistic beam and a uniform central core with a log normal intrinsic energy distribution. And so the energy distributions of 2011-24A and 1211-02 fall within our bimodal regime. And this allows us to constrain the plateau size and the parameters of the intrinsic distribution and possibly the value of the Lorentz factor. And it's my talk. Thank you for listening.
Thank you, Clarinda, for the very interesting talk. Do you have any question? Yeah.
Hi, Clarinda. Excellent talk. I was just wondering if you have any sense of which physical model could be consistent with the observations for the two repeaters that you saw, or you fit your data for.
We haven't actually looked into that yet, but that is something we're keeping in mind for a bit later.
Cool. Thank you.
Hey, Clarinda. Really nice talk. So I was thinking, what motivates you to add a plateau to the beaming shape? So is it theoretically motivated, or what is the idea here?
Yeah, without the central beam, we weren't able to actually create a secondary peak. We tried with a bunch of different functions, but without creating a more complicated function, the easiest way was to just add in a central core.
Right, thanks.
Hey, Ramesh?
Yes, can you hear me?
Yes.
Yeah, thanks, Clarinda. That's a very interesting presentation, and it's quite amazing that you were able to look at this as a short project. So my question is that I understand that right now you only have like a limited number of these distributions, and they are not super constrained. But
Yeah.
you also mentioned in your framework that you have to fiddle with this Doppler factor. So I was curious if, that assuming that you have like, that well-determined shapes, are you able to constrain that, or is it something like you are putting in some reasonable numbers at the moment?
We initially tried with a range of different Doppler factors. What we found with the at least the power law is that it didn't change the actual observed energy distribution too much. It could change with a more complicated function, but at this stage it hasn't really given us too much extra, so we've just kind of left it to the side.
Thanks. Yes.
Hey, thank you. The next question is from Paz.
Hi, thanks for the presentation. I wasn't sure if I got it correctly on your slide. It passed pretty quickly. But in the Doppler correction, are you taking the Doppler to the first power? It looked like you have one factor.
Yes, we were just doing one.
1 minus beta cosine theta. So I would think that you would need Doppler to the third power if you're looking at the flux per unit frequency. That is how it transforms from the intrinsic amount that is emitted to what will be observed at some arbitrary angle. So
right, that's a good suggestion. We haven't thought about that yet. We were just kind of trying to do the most simplest thing to get a bimodal energy distribution, but now that we've actually got it, it's kind of free range, so we might try that.
Okay, no, if you want, we can talk more about the physics, because there are very specific ways that you can get this transformation. It's the nice thing about it is that it's not arbitrary. It's completely defined by relativistic kinematics.
That would be good.
Thank you.
Any other question? Okay, if not, let's thank our speaker, Clarinda, again. Thanks a lot for the very nice talk.